So the parallel component is associated with the mirror formula. Right? When you write the mirror formula, that 1 by u plus 1 by v is 1 by f for the paraxial approximation. The u and v actually represent the distance of object and image with respect to pole of the mirror. Show the mirror. So these are the value with respect to mirror. So when you differentiate, what you get is the velocity with respect to mirror, not ground frame. So minus 1 by u square. And this is basically your du by dt. Do you realize this? This is difficult. So basically, when you write du by dt, you mean actually u parallel. You don't mean u in general or u perpendicular. You only mean the longitudinal component. So this is what it represents, and this is called a velocity of object with respect to mirror along parallel to the principal axis. That's how we represent. And this is 0, so this will give you the velocity of image with respect to mirror equals to minus v square by u square into you can just this one. So this formula we are deriving this formula. What we are trying to understand is that this is the v parallel component. That is, of course, velocity of image with mirror. So this is the longitudinal component, only longitudinal component. So you can also write this as a magnification square, and VOM is basically your u not cos theta. So this is what we are assuming, that this is the velocity. If the mirror is at rest, then this is the velocity in the mirror frame also, in the ground frame also. If mirror also starts moving, then I need to change the entire way of writing this. So in such case, what we are going to write? Velocity of object minus velocity of mirror. And the velocity of object in this case becomes u not cos theta. And this is the velocity of mirror. Again, you have to, from the context, you have to substitute the value. That's why I'm not putting things here as of now. Clear?
Yes, sir.
Yes, sir.
And for the other motion, like the transverse component, the magnification formula we use, which says that it is the height of the image upon height of the object. So height of the image, I mean, the better way of writing would be, because object height is, I mean, let's say fixed or maintained, or maybe you can write like this. So the yi is basically magnification times y naught. So the to get the transverse component of velocity of image, you have to differentiate m into y naught. And m is definitely not going to be constant. So m itself is variable. That is what we need to realize. So this is the VIM transverse. And this will have two terms, m times du y naught by dt plus y naught times dm by dt. Understood? So this was the discussion. So I think we can end the discussion on the reflection from the mirror, and now we can move to the refraction, right? From reflection, we have done the vector representation of the vector law of reflection. Have we done the vector way of writing the law of reflection?
Yes, so we did.
Yeah, so we have done the. So now we can start the refraction. So refraction in our syllabus is meant for refraction from plane surface, or you can say plane boundary. And later on, we are going to learn the refraction from the curved boundary, especially the curved boundary will have the spherical curvature. So that is the part of our syllabus. So the phenomena of refraction happens due to the change of dielectric medium. So whenever the light is traveling from one medium with one, when I say one medium, what does it mean? I mean one particular electrical and magnetic property. So medium basically refers to, or a medium is known by its electrical and magnetic properties. So like the term which you have studied already, the dielectric constant and something like that. Later on, you will also study about the permeability. We have already seen the permittivity. So these are the terms which are able to define the electrical and magnetic properties of medium. And whenever there is a change of it, let's say if you go from one medium to another medium, we know that the electric field will suffer some changes. So the electric field actually changes the direction as well as magnitude while going from one medium to another medium. And why this happens? It happens generally due to the induction of charge at the boundary layer. So the boundary layer of two media always generates the instantaneous induction process. I mean, what you say light is basically the electromagnetic wave, and the electric component of light always interact with the medium part, and that interaction results into the creation of some dynamic surface charge, and that dynamic surface charge creates or alters the electric field direction, which in turn affects the direction of motion of the light, or the direction of motion of the of propagation of the light energy. You can say the direction means the direction in which energy is propagating, that will alter. Okay, so that we translate into the chapter of geometrical optics as a refraction. But essentially, I mean, technically, what is happening? The refraction is happening due to the alteration of the electric components. Generally, magnetic components do not get altered in most of the process. So it is the electric field of the light and the electrical component which alter during the passage from the one medium to the other medium. And the interface, which is quite a mysterious place, undergoes some sort of induction, or you can say polarization actually, and that in turn changes the electric field component. Okay, so you will come to know that in advanced uh, stages, that okay, we have something called boundary condition, and for any boundary, the electric field, if we having two components, the parallel and the perpendicular. So while change going from one like side to the other side of the boundary, let's say we have a like this. So the moment you enter from the one side to another side, what really happens? The parallel remains unchanged, but the perpendicular changes. It may shrink, it may expand depending on the relative medium. So generally, when you go from the rarer to denser medium, what you will see that the E perpendicular will shrink in size. Okay, and because it will shrink if you go from the rarer to denser or something like this, it may shrink or expand. We don't know that. I mean, yeah, it depends on the charge induced, whether it's a positive charge or it's a negative charge, and that in turn actually changes the direction of propagation of light. Okay, so direction of propagation of light follows the Poynting vector, which is written as E cross B. So let's say the magnetic field is having some direction. Electric field, if we change the direction, the E cross B will effectively changes the direction. Okay. So it is all about the E and B component on the two sides of the medium, which eventually decides that how the energy is going to propagate, and that we interpret as a phenomena called refraction. So what is refraction? This is called Poynting vector, which decides the direction of flow of electromagnetic energy.
Sir, is it S?
Yeah, it is S. So it will dictate the direction of propagation of electromagnetic energy. And if you remember, in the very first lecture, I said the ray optics talks about the direction of flow of energy. It never talks about the field or the wave and all those things. What we believe, the ray basically represents the direction of flow of energy. That's it. So refraction in a very simple term is defined as refraction. It is the bending of light while moving from one medium to another. So it's basically bending phenomenon. And how it is accomplished is not our requirement to know in detail. But on a very basic level, you can understand it is the electric field interaction. So the question is, what is medium and how we distinguish or classify that this is one medium, this is another medium? Is it the shape, size, color, or it is something else? In many cases, we know that the medium can be transparent. Now, transparency is a concept which means the light can eventually make its way through the medium, and therefore you don't see the medium, you see nothing. That's called transparent. So you have the perception of something, but you cannot see it. So light is coming from that side, so it carries the image on the other side. So what you end up seeing is the image carried by the light. The medium's image is not found. That's very interesting. So when I say a medium, what I mean is the characteristic and you can say one unique combination of electrical and magnetic properties. So let me just put in words. A medium, and you should know all this small definition. A medium is characterized by electric and magnetic. So a medium is characterized by its unique electric and magnetic property. So one medium will have one. So let's say if we have a medium in which the property is continuously changing. In such scenario, we define something called variable refractive index. Now the refractive index is a measure of variability of a medium, or it's a measurement of, you can say, the electrical and magnetic property of medium. So eventually later on you will study that, okay, the refractive index is a way to represent something more deeper than what you just believe. And then there is a very complex relation of refractive index with polarization, with electron, with oscillation, with frequency. So the refractive index is a function of variety of things. So n is a function of charge, frequency, uh, polarization, the number density of free charge carriers, and so many things. And then all this complex event is packaged into a simple name called n, and it comes with a number, let's say a number more than 1, 1.3, 1.5, 4 by 3, 9 by 8, 2.4, 2.3. So this number is basically we are trying to create a dimensionless quantity, a quantity which depends on all these complex things, but eventually we express in a such a nice way that it looks like a simple quantity. So again, that's not part of our syllabus. We will not go deeper into how exactly it is expressed. If you're curious enough, you can just search Google the refractive index, and you will see a very large complex oscillation relation, differential equation which describe it eventually. So a medium is characterized by its unique electrical and magnetic property. That's it. So when we say you go from medium 1 to medium 2, when I say that you are going from, the light is going from medium 1 to medium 2, what we really mean? We are entering a region with a different composition of molecule, giving rise to different electrical and magnetic property. That is a mean. So what exactly is boundary? How to define boundary then? Or interface? So what is boundary?
The surface of interaction or interface of interaction between two mediums.
But boundary is imaginary, na? So you go from medium 1 to medium 2, what you see, the change in the electric value, the magnetic field value. Now the question is, the electrical and magnetic property are well defined for two medium, then what is the property of boundary then? And is the boundary refers to a single layer or few atomic layers here and there?
So few atomic layers.
Yeah, it is always. So always remember that I have explained this in past also. The concept of interface is quite challenging. A boundary is the overlap actually. It is the region in which the properties are not well defined. So that is the first thing we need to say. A boundary is the ambiguous region. So what we say, That boundary is a region in which the electrical and magnetic property changes abruptly. So you go from one side to this side, then the properties are well defined on the two sides, but not during the transition period. So we say boundary is also a region. It is a volume actually, up to few atomic layers, in which the properties are changing abruptly. So that's the definition of boundary. Boundary does not mean that your own idea of the imaginary layer and something. It is physically present actually. So let me just put a definition for boundary as well. So what is boundary? It is the region between two media in which electrical and magnetic property changes abruptly. I hope this is clear, guys.
Yes, sir.
So these are definition. A medium is not just like the air, water, and whatever. A medium is a composition of what molecules. So generally, we assume the composition is homogeneous, and a homogeneous composition will also refer to the homogeneity of the properties, and the homogeneity of properties will also manifest that the refractive index is constant. A
Sir, I
non
didn't understand boundary.
So what is boundary? It is a like a region in which the properties are changing abruptly, because on one side we have the well-defined property, on the other side you have well-defined property, but the properties of boundary is not well-defined. That is the meaning ambiguous region. Understood?
Yes, sir. So we won't be able to calculate
No,
in
no,
that
nothing,
way.
nothing. You have no, you have like no control over what is happening in the boundary. So boundary is something that we cannot understand. I mean, this is like when you touch the water. Let's say you put your hand in a bucket filled of water. You never know that when your hand was not touching and when it is touching exactly like the gap. So when you come very close to the water surface, there's some water molecule which is leaving the surface and touching your hand anyway. So the physical connection starts much before than you can think you're starting. Okay. So we never know that when the boundary one ends and other begins, because the atoms gets diffused in that location. I mean, you cannot say that this is ending, this is beginning, because there is nothing like a flatness, right? We always have the irregular surface. So maybe if the upper surface is like this and this is like this, can you say where the boundary starts and where the boundary ends? Can you say that? You cannot say that. So this is the boundary 2, but if you go further, this is the boundary nothing, boundary 1 maybe, boundary 2, boundary 1. See, at the same on a horizontal line, if I draw, I can get both boundaries, right? Isn't it? Can we say which boundary I'm talking about?
No, sir.
We cannot say. So boundary belongs to nothing and no one. It means it belongs to both. That's why we call boundary. Understood? Okay. Anyway, so the whole idea of medium is clear. I hope so. The reason behind the refraction, the way we study in ray optics, is determined by the Fermat's principle, if you remember. Okay. And because because we are defining the boundary as a reason in which the things changes abruptly, So and bending is all about so refraction is all about bending of light. So when we say there is no refraction, so what is the condition for no refraction? Condition for no refraction. Now, what is interesting is that whenever we have a medium, let's say this is a medium, if the propagation of light is happening exactly perpendicular to the boundary, if this is the direction of propagation of light, you will come to know from the mathematics or from the properties of electromagnetic wave, the direction of propagation is always perpendicular to the electric field and magnetic field vector both. So which simply means, let's say I'm talking about the polarized light, just for your idea, the electric field only going to be perpendicular to this direction. It could be anywhere, but in this, it is always going to be perpendicular. And now, if it is perpendicular to the direction of propagation, so for boundary it is parallel. And now here we do not have the perpendicular component. Okay, so for this medium, we only have only one component. And again, in the advanced maths, you will come to know in physics, the parallel component across the boundary remains unchanged. That's the whole history. Just so now what I'm saying is that the electric field component, in this case, the only component which will exist is the parallel component, and parallel component never changes across the boundary of a region. So we say that because component is not changing, so the light ray will still remain normal to the, and therefore the light ray will keep on moving across the medium. And if it is facing a boundary which is always perpendicular to the direction of propagation, the light will never suffer the change in the component of field and hence the direction, and therefore the light will just pass across it. Now this is called condition for no reflection. So condition for no reflection is obvious when the the angle of incidence is 0 to the boundary. Okay. When the angle of incidence is 0 with respect to, so as long as the light ray is getting incident normal to the surface, it will not suffer any reflection. Now this is some sort of debatable in across academia, that should we call the reflection as bending of light, or should we call reflection as the change of magnitude of speed of light. So it is controversial, but as far as the JEE is concerned, we'll keep this assumption that the bending refers to reflection. Okay. So the speed will not be the criteria to understand the refraction. Even S. Verma in some of his videos has trying to claim that okay, it's the bending is there as per the because the speed is changing, but the refraction what has come from the bending. So unless it is not there, we will not believe what even Verma ji said. So for JE, keep in mind that the bending means refraction. No bending means no refraction. That's it. Okay.
Sir,
Uh,
that E perpendicular is the resultant of electric field,
yeah, yeah.
or
See, if the light ray is coming this way, this is the light. So the component will be, so there will be two component. One will be like normal to the plane. Another will be like perpendicular to the line. But in each case, you can see both are perpendicular component, right? Now, if the imagine this, if the boundary is coming is not in its path perpendicular, if the angle of incidence is non-zero, so for the boundary we can have component. No? You can see. So it is like you can resolve the vector. So this E will have two component. You can say E perpendicular and E parallel. Yes or no?
yes, sir.
Now what I'm saying is the parallel component remains unchanged, but the perpendicular will change actually. Okay. So when you enter the region, the direction of the light will change because let's say you enter a denser region. So denser means what you have learned before that denser means. So denser means the dielectric constant is more actually. That's the meaning of denser. More the refractive index. So dielectric constant will increase. So electric field needs to increase actually. So the perpendicular component will even become bigger actually. And the parallel will be remain
Unchanged.
unchanged. So as a result, you can see the net electric field direction will be now it is towards. So I mean, how I need to draw is I need to prove that the electric field line is the net is something perpendicular to like this. So the new field will be
Yes, sir.
something like this. So it will be oscillating this way. Now just let me draw first, then we can understand. If this is the field lines, then I can guess whether it will increase or decrease. So one component is into the plane, which I'm ignoring, and other is like this. Now, if you look at this component, and if I draw a line here, the horizontal component, the E parallel is still same. Sorry. But you can see the E perpendicular has decreased. Can you see that? So E perpendicular has actually decreased in this case, and that's why the direction has entirely changed. So what you call the propagation of light is basically propagation of energy, and the propagation of energy is entirely determined by the electric field component. So a boundary is something which can which can undergo the polarization process, and by the virtue of polarization, it will effectively change the electric field component which is perpendicular. And because if you know polarization creates the plus and minus charge, and plus minus charge can create the field. So near any boundary, if you remember, near any boundary, the if it is a charge surface, the field is always perpendicular. If you remember, sigma by 2 epsilon. If you remember from the electrostatics.
Yes, sir.
So boundary charge can only affect which component, the parallel or the perpendicular.
Perpendicular.
Exactly. That is the reason that the perpendicular gets affected, which in turn changes the direction of propagation of light. Understood?
Yes, sir.
So the light is bending is as good as saying that the resultant field is changing. And it is up to your interpretation, how you understand this. Again, I will not go deeper into all this because even I don't know much about it. So I have studied all these things in past, but because it's not part of JEE syllabus, over the years I have forgotten most of the things. These are some very vague ideas which I have in my brain, left out, and I'm just sharing with you guys. So you can understand, at least you can understand that how medium is affecting the direction. And now you also understand that why it was not happening in the previous case. Is it possible now in this case? So in this case, the field itself is parallel to the boundary, so it don't have the component, right? Can we have the perpendicular component here?
No, sir.
And because we do not have the perpendicular component, so there is no question of getting affected. Understood? So because the perpendicular is not existing, so it is not changing. That's the whole idea. So anyway, so as the light propagates, basically there are many ways of looking at light. I mean, the refraction phenomena through a medium is very interesting phenomenon. The light which hits the boundary never comes out. That's the first event. So when you see that, okay, light is entering the prism, coming out of it, the reality is the light which has entered never came out. Yeah, what came out is also a ray, which entered was a ray, but what went between, no one knows. And also you cannot see the light ray in between, in the part of the prism. In the books, in most of the books I have seen that they draw the wrong diagram, wrong picture, that what they do is they draw the light ray entering the prism, and then they continue the light inside the prism, and then they show the light leaving. The reality is what? You can only see the light entering the prism and exiting. You cannot see in between. Do you know this fact?
Yes, sir.
You cannot see the light entering the lens also. You can see it is hitting the surface of lens and coming out of it. You cannot see light ray in between. And the reason is the light which enters is like the oscillating electric field, and the lens, prism, slab, what you call transparent medium, they have molecules which are capable of oscillating at a same frequency as that of the incident electric component. And as a dipole oscillation, they regenerate the energy. And that energy is transferred from the one dipole to the other dipole. So we transfer it from one dipole to the next dipole, which in turn transfer from the next dipole. And the last dipole re-radiate back to the space actually. So that is the actual phenomenon. And of course, I mean, the light never exits what enters. In fact, the light interacts with the surface. And as a result of interaction, they undergo the oscillation process. And why why it undergoes oscillation? Because light is high frequency wave. But that is a wave interpretation of interaction, which we are not doing right now. What we are doing is the ray interpretation. And that's why going deeper will confuse you. So just keep it simple. Okay. Okay. I think so far, if you have any doubt, you can ask. I'll just go to the next one. So what we mean by refractive index, and of course it's a complex topic. What is refractive index? It is like a good packaging of some very complex event happening inside So the refractive index is actually a manifestation of that how the interaction has occurred at all among various you can say parameters like the charge density of a medium, the molecule packing density, the strength of electric field, the frequency of the incident wave, and there's so many things. So what you will learn that the refractive index is not a property of medium alone. The refractive index is a property of medium along with who is interacting with the medium. Now, what does it mean? So, if you say the refractive index of a glass is 1.5, what does it mean? Is it really 1.5? The answer is no. It is 1.5 on average for the white light. So, it is on an average for the white light actually. Average value. What does it mean? Every component of light will have different frequency. And the change of frequency will change the interaction criteria. So the energy will not propagate with the different frequency in the same fashion. So as you change the frequency, the energy propagation through the medium will get affected, and therefore the light speed. See, what we call speed is nothing but the rate at which energy is propagated. So the speed of light is a function of frequency, and therefore the refractive index is not merely property of medium. It is the property of medium and the wave interacting with the medium. Are you getting my point? Yes or no? Hello, hello, 1, 2, 3.
Yes, understood.
So can we say that every medium will have one refractive index? Yes or no?
Sir, one refractive index.
So one medium, one refractive index is correct statement or wrong?
Wrong.
Very good. So what will be the correct statement in this case?
A pair of media.
Okay. No, so we can, let's say if you have a medium and if you have vacuum, we can still compare, no?
Ah, yeah, that we can do. But we can't say for one medium like
Yeah, so
this.
but no, that's called the absolute refractive index. When you define something with respect to the maximum velocity of light, see the maximum speed of light is c. Now that's for vacuum or for rarefied air. What about the medium, which is not as rarefied as air? The refractive index is defined, isn't it?
Yeah,
Now it is defined for the medium or it is defined for something medium and something else? Okay, I think my question is not well put. My question is, okay, my question was that can we say that one medium will have one refractive index? Can we define the refractive index for medium? Yes or no? That was the question.
Yes, sir. Yes, sir.
Yeah, we can define the refractive index for a medium, but can we define it uniquely?
So I didn't understand. Like,
Yeah, exactly. I mean, see,
sir, yeah,
uniquely
we
means
can define it uniquely.
no, that's the problem. We cannot define it. Refractive index is defined only for one medium with one wavelength. So one component of light will have interaction with the medium and will have one refractive index for that component. Another component of light, see, what is the meaning of component of light? Their classification is based on frequency, yes or no?
Yes,
So when you say a white light, it is actually having seven different composition of frequency, isn't it? In fact, much more than that, but we have classified broadly into 7 categories. Okay. So every component of light will have same frequency or different frequency.
different frequency.
So how they can interact in a similar fashion? Tell me, yes or no? Will they interact in a similar fashion?
No.
And if frequency is different, then we know from the chapter of SHM, energy is square of frequency, yes or no?
Yes.
yes,
So the the propagation of energy with respect to the sense of frequency cannot be same. Na? So the rate at which the energy will propagate in a given medium depends on what kind of frequency is interacting with the medium. So the refractive index of a medium is defined for the component of light and the medium as one pair. So one lambda, one refractive index, or one frequency, one refractive index. And that is the whole idea of the dispersion, which you will study later on. The dispersion is because of this particular phenomena only. No? So when the white light enters the lens, what happens? All do not face the same mu. No? All face different mu. And as a result, the bending occurs differently for different component. And that is why it is splitting into the rainbow, right? Or the spectrum. So why the light will disperse in a medium? Because medium will treat every component differently. And the ability to bend each component will vary, isn't it? So all component of light, every component will have different set of electric field oscillating. And not only that, even the frequency will be different, as well as the magnitude of each component will be different. Later on, you will come to know that electric field component we write only for one frequency using the concept of the traveling wave. If you remember the traveling wave equation, E equals to A, Y equals to A sine omega t minus kx. Do you remember this from the wave chapter? Y equals to A sine omega t minus kx. Traveling wave.
Yes, sir. Yeah.
So here you can see the omega is saying that one particular component will have one electric field amplitude, and so it is one component. I mean, this is the field of one particular component of light. So for 7 components, we have 7 different values. And not only that, the omega will also change. The k remains same, but omega keeps on changing. So if you write the electric field of 7 different components, you have to deal with 7 different frequencies. Do you realize this? And therefore the energy propagation will change. So what is the formula of the Poynting vector? So Poynting vector is the amount of energy crossing a particular cross section per unit area per unit time and so on thing. So as E will change in terms of frequency, this answer will change actually. So all energy will not propagate through a medium with the same speed. So the refractive index is defined for a pair of frequency and medium taken together. I hope I'm clear what I'm saying. So refractive index is defined for what? A single medium or a medium for a given frequency. What is the performance of a school? Is it the school performance or performance of the student in the school?
Students in this.
That's common sense. So school is like a medium.
Yeah.
Now, of course, we need school to represent the performance, but it is the student whose performance eventually decides the performance of the school. And every student will have different performance. I mean, not exactly, but quite a lot different. So every student will, every component will have different frequency, different amplitude. They will interact in a different fashion, and then there is an overall interaction. So we define when we quote the refractive index in when you read a book, a textbook, you say the water is having the refractive index 4/3. You would never realize that what was written there was actually meant for the white light, and that was the average value. Okay. So you know how we find the average value? It is the refractive index of the violet plus red upon 2. That's how we define. or sometimes we define as the yellow. So yellow is the average frequency among the Vibgyor. It is taken as standard, and the refractive index corresponding to the yellow light is taken as the average in many calculations. So there are two ways of thinking. Either you think this way or that. Are you getting the point? What I'm saying? Hello, hello, hello.
Yes, so
Yes, sir.
Yeah, I know it is something you're learning for the first time, so you may be confused of what is this. Okay. So not very regular thing, but it's okay. So let's define the refractive index, the average value. Okay. So velocity of light in a medium is how much? And see, this idea is very powerful. Like when you will study eventually the dispersion phenomena, you need to understand this concept only. That every component will have different refractive index. We have something called the Cauchy's theorem, which I'll come to that in this topic only. And the Cauchy's theorem is the relationship between the mu and the lambda. So what is the velocity of light in vacuum?
C.
It is 299
To 10 raised to 8.
792,458 meter per second, right?
Yes.
So this is roughly right as 3 into 10 power 8 meter per second. You can remember this is nice number. So in high school, how you study? What is refractive index?
Mu is equal to C by V.
So that's called
Like,
the absolute refractive index, right?
yeah,
Absolute we define with respect to vacuum.
yeah.
So the dependency of this C is called the electromagnetic constant or electrodynamic constant, also called the Maxwellian constant. And when Maxwell was studying the electromagnetic wave, he came across this number. And when he calculated the number, he was surprised to know that this number matched the number which was already derived from the experiment by the Fusio and Foucault. The Fusio and Foucault. Now that's if you read it, it's Foucault and Fusio, right? Foucault is called Foucault. These are like Italians or French guys, and their names are like this one. So they had the calculation of light, and actually Maxwell was not aware of those calculations. He was working on the electromagnetic wave, and through the Gauss law, Ampere law, Faraday's law, he arrived at a new constant of nature. And what was surprising that this constant exactly matched with the experimental value of speed of light, and that led to the interference that light is an electromagnetic wave. So that was the first time when the world realized that light is an electromagnetic wave, because this is not a simple coincidence in nature. Okay, so C is not actually speed of light, but later on, because of the equivalency, the C was mostly adopted by for writing the speed of light. because of course numerically it's the same. So C was actually determined using the Maxwell's equation, or it came from the electromagnetic theory. Of course, this was first of all derived by the Oliver Heaviside. So he was the mathematician who actually formulated or created a new mathematics called differential calculus. He used the term like del operator and so many things. So he has been credited for a variety of discovery, and he made the Maxwell equation in a really simpler form. So there are two forms of Maxwell equation. One is called the integral form, which we study in the JEE, and the differential form, which I will teach you. In BTech, you will have to study the differential form mostly. The integral form is only for the class 12. Anyway, so the refractive index, C is this value. The speed of light in any medium, how we write? So the mu is called permeability of medium, and permeability represents the magnetic property. And then comes the epsilon, which we know already from electrostatics. It's called permittivity of medium. And this is called the electric property.
Sir, epsilon naught is for vacuum.
Yeah, that is for vacuum. It is for in medium, any medium. Now, the definition of a refractive index is simply defined as the ratio of speed of light in a medium, because we're talking about the medium, upon vacuum. So the simplest definition is V by C, but the V we can write as mu epsilon, and C we can write as so it turns out to be mu naught by oh, what I my God, so much blunder. Huh? No, what I have done. N is defined as C by V, and that is why N is always more than 1, because C is always more than V. So now we can write as 1 upon mu naught epsilon naught, and C is mu epsilon. So N is this upon this, and mu upon mu naught is called mu R, the relative permeability, and this is a relative permeability, which is also called the dielectric constant. And basically, the when it comes to the interaction of light with medium, the magnetic property plays almost no role. So we are happy with the electrical property only, and we say that for non-magnetic medium, so let's say if a medium is only manifesting the magnetic property, because most of the dielectrics do not exhibit the magnetic property, except if you talk about the ferromagnets or the paramagnets and diamagnets. But in nature, if you have paper, plastic, kerosene, water, they do not have the magnetic properties. Okay. So if we have a ferromagnetic liquid, it will of course have the magnetic property, in fact, quite dominant property. And those things we never use for the light propagation, right? So for non-magnetic medium, the relative permeability is taken as 1. Oh, we don't take 0, keep in mind. Okay. And therefore the n will be equals to under root of. Now it is again not necessary that we should always think of the reflection due to the white light. In fact, even a stone, if you have a stone which is completely opaque, will also have the dielectric constant, and it will also undergo refraction, of course not for the white light but for the maybe the light which can enter. Let's say X-ray can enter easily. You may think of the infrared wave also. So those light can also undergo those kind of any electromagnetic energy will suffer refraction. It is not just white light. Okay. Now white light when interacts with the bodies called transparent bodies, you can see the bending clearly. So you can have X-ray which can also undergo bending phenomena with some other medium, some other different types of molecular structure. So it's quite a complex thing. The epsilon r is called dielectric constant, but it is not the same as you studied in electrostatics. So in electrostatics, what you should is called the static value of dielectric constant, and the static value means when the medium interacts with the static electric field, it will exhibit one behavior. When the same medium will interact with the dynamic field, a field which oscillates or changes abruptly and very fast, the interaction will change, and therefore the epsilon r for the dynamic field gives you a different value than the static. Okay. So always keep in mind that the epsilon r depends on the nature of interaction. Okay. So static field answer, let's say for water we have studied it's 80, roughly 80. Don't put here 80. It will give you then roughly 9 refractive index for water, which is not possible. For water we know it's 4 by 3, 1.33. So what I'm saying is the refractive index, the dielectric constant of a medium depends on the nature of electric field. Static field gives you different answer and dynamic gives you. So what we can write here as a takeaway, we must mention here that epsilon r, the dielectric constant of a medium depends upon what? Upon nature of
Medium.
field. So the static electric field and the dynamic generally oscillating. So dynamic electric field will give different value of epsilon r. So don't think that okay, the static we said 80 is not for dynamic. That's why the answer will have very different answer, right? Okay, we know it's roughly 4 by 3. You can take the square root of 1.33, you will get some answer. So that is the potentially the value of epsilon r. We have some well-defined formula for that also, but okay, I will not go into that. Okay, so I hope this refractive index concept is clear.
Yes,
So
sir.
we have something called the relative refractive index. So relative is you define the velocity in the two medium. So let's say n12. What is n12? n1 by n2. So it's like n of 1 with respect to 2. So because we are trying to find the with respect to 2, we have to divide by the 2. So n1 is what? C by v1, n2 is what? C by v2. So n12 turns out to be how much? v2 by v. So the ratio of speed of light in the second medium with respect to first medium is the refractive index of the first medium with respect to second medium. So if you enter denser medium, the V2 will be less than V1. So N12 can be less than 1. So relative refractive index can be less than 1, more than 1, or equal to 1. So we are talking about a relative, which is possible. Absolute is always more than 1. In fact, I mean the actual formula of this epsilon r is something like 1 plus big complex terms here. So it always comes more than 1. So that's why no matter what you do, you are going to get answer more than 1. I'll give you derivation sometime because the derivation was part of international Olympiad competition. But they had given all the prerequisite that how to derive it. So they gave the entire comprehension of 3 pages, which every student was supposed to read and derive in the international Olympiad competition. In JEE, of course, such comprehension is not possible because they have 6 hours to solve 6 questions. Okay. Any. And we have to solve the how many questions in 3 hours? So 1 hour 30 questions, right? 20 questions. 25. Okay. So these are simple things. Let's do it quickly. Snell's law of refraction. So Snell's law of refraction, we are going to study for the plane interface. Now I have no idea whether the medium second is denser or and here the density, when I say denser, what does it mean?
Optically denser.
Yeah, and optical denser means the speed actually. So any medium in which the light can move faster comparatively, we call rarer medium, and the light can move slow, we can call denser medium. So optical density is taken, not the physical density. And density actually refers to means speed. That's it. So more the speed, lesser the density. That's simple logic. So after entering the medium, it could be like this, or it could be like this. So it depends on whether the boundary is having the positive charge or negative charge. Things changes. So N1, N2, we can say the refractive index of the each medium. This is called the angle of incidence. This is the normal to the point of incidence. This is the angle of refraction. Let's take N1. And light goes from one point to other point in the shortest time. And because if the N2 is denser, let's say, so to reach in the shortest time, you will try to move more through the rarer medium and less through the denser. And that is also visible if you draw a line joining the start and end. You can see. So what we have done, the displacement is this line, but we have traveled more on the rarer medium and less on the denser. I hope you can see this. So this I discussed in the
Yes.
very first lecture in the lecture of reflection. There only I explained the principle of least time, and this is called the Fermat's principle of least time, which can give you the relation. And what is the Isner's second law? The first law is that incident ray, normal, reflected ray all lies in the same plane. So that's very much known to all of you. Okay, let me just mention this quickly. The incident ray normal at the point of incidence and the refracted ray, just a moment. Okay, so you can say this. So Ni multiplied by N1 multiplied by sin I and N2 multiplied by sin R, this will remain same. But this is only true if the medium is parallel. The boundaries are parallel. If the boundaries are not parallel, then for one pair we can write like this. For other pair, we need to again recalculate the I and R. So what does it mean is, if you have multiple pair of media, so as long as the all boundaries are parallel to each other, then the Snell's law doesn't need to be written only for the consecutive pair. You can write for the first and the last also. You can write between here also. So if it is a vacuum, so n will be 1. So if this is, let's say, alpha, this is beta, we can directly write, what we can write? 1 sin alpha is n for sin beta. So as long as these are parallel, you can just write like this. And it's not difficult because because these are parallel. So the angle of refraction of any boundary will be the angle of incidence for the next boundary. And that is the reason. Say, if you draw a line like this, so you can see clearly that R of the first is the I of the second. And that is the reason it will continue this fashion. If they are not parallel, this will never happen. Isn't it? That's logical.
Yes, sir.
Yes, sir.
Only for the pair, only for the media which are parallel to each other, you can write between any two without worrying about the intermediate values. And if the initial and final pair are same, then answer is also going to be same. That's very logical. So no matter what happens inside or in between, assuming TIR is not happening, yeah, that's also something which we have to be careful about. Okay. So our first topic will be, of course, that's the first topic for everyone. Refraction through glass slab. It's not slab, it's slab. So glass slab is particularly, the way of thinking is a medium with at least two parallel surfaces. So imagine if you have a medium So you can see that slab need not to be like, it should be perfectly like a cuboid or cube or something. A slab only means if I have at least two surfaces which are parallel, my job is done. We can call it a slab if the light ray only uh, refracts from these two surfaces. Okay. So imagine we have a medium which is surrounding the slab. So I always want to derive the formula in general, not only for the situation which is called the air and the medium interface. So always try to make it in general. It's very bad. Anyway, look what I'll do. Let me make it simple. I'll put like this. Okay, so in a slab, what is the condition for slab? A slab is a medium bounded by any number of surfaces in which the light ray suffers refraction from two surfaces which are parallel and planar, like planar and parallel both. So the rule is any medium bounded by any number of surfaces will act as a slab if the surfaces through which refraction is taking place are planar and parallel to each other. That is the meaning of slab. So how you can connect? Who will tell you how to write? Can you repeat what I said?
So can you repeat it once again? I did not process it.
Any medium bounded by any number of surfaces. So I have no like idea whether it's a diamond with 64 cuts or 128 cuts or 256 cuts, or it's a simple cuboid, or it is any random slab with uneven edges. So the idea is, okay, let me put it in writing actually. A medium with any number of a medium bounded by any number of surfaces will act as slab if the surfaces through which the refraction is taking place, if the surfaces through which refraction is taking place are planar and parallel to each other. Now what happens if they are parallel, planar but not parallel? So any medium in which the light ray is passing through two surfaces which are plane but not parallel to each other, what we call? Am I audible?
Yes, sir, you're
Sir,
audible.
can I repeat the answer?
If the light ray is passing through two surfaces which are planar but not parallel to each other, what we call such medium? That is called prism. What is prism? It is same as slab, only difference is in slab we have parallel surfaces, in prism we have non-parallel surfaces through which light refract. Do you realize this?
Yes, sir.
So for a medium to behave as a prism, what is the prerequisite?
The surfaces are not parallel.
That's it. But they should be plane.
Yeah,
And when a medium behave as lens,
when they are neither.
when at least one of the surface is curved, so we do not need flat both side, at least one side should be non-flat. It should not be flat, it should be curved. So the moment you make one surface as curved, it automatically becomes what it becomes?
Lens.
Lens. So see, lens, slab, prism, these are not something extraordinary thing. Like you should not be bothered about all these naming convention. The chapter of ray optics is only about two things. In fact, one thing. The entire chapter is designed for only one purpose, that is bending of light. Now, in reflection, you use the law of reflection to understand the bending, and in refraction, you understand the Snell's law. So the crux is, if you can really understand the Snell's law, and if you're able to apply it, you're done with the chapter. So all formulas which you have seen or you will be seeing in this course, all we can derive from the very basic Snell's law and the law of reflection. Nothing advanced we need to solve any question, even the lens question I'm saying. So even the lens questions are derived using the Snell's law. Lens formula comes from the Snell's law. The prism relations comes from the Snell's law. So there is technically only one law for refraction and one law for reflection, and that is the base for everything. So don't look as a chapter with topics like this. Look as a event, and there are just two events. And the key to derive any formula is check the number of reflection and check the number of refraction which light suffers. And as many reflection, you need to write the law of reflection as many times. And as many refraction, you have to write the laws of refraction that many times, or you have to use the Snell's law that many times. And that is the whole idea. If you can understand this, you're done with the chapter. Okay. The entire syllabus is this much. Okay. And these naming, slab, prism, lens are all based on some geometrical properties. That's why the chapter is called geometrical optics. So I'm going to use a lot of geometry, and I will be using simple laws of refraction. That's it. Okay. So let's start the slab question. So let's say we have an incident ray. So I'm making it too much oblique. And what will do? You will just draw a normal at the point of incidence. You have no choice. So technically, we are going to assume that the medium surrounding the slab is less denser compared to slab. It is not compulsory, but it's good to start with. So the mu surrounding the medium is less than mu. Generally, we have air, but I'm trying to, again, as I said, we are trying to derive everything in a general fashion, not individual fashion. So let's say mu m is less than mu and the light is entering. This is the angle of incidence. You have to learn the derivation to master this chapter. And then you will enjoy this chapter. Else, if you think only formula as a chapter, it's very difficult. Now, assuming the medium as denser, what do you expect? The light ray will bend towards the normal or away?
Towards.
That's logical. It will bend like towards the normal.
Yeah.
Now, as it will travel, it will have a normal life living in a medium. But the moment you try to leave the slab, you have to change the medium, which means you have to suffer one more refraction. Yes or no?
Yes, sir.
So as many refraction, as many times you have to write this Snell's law.
Yeah.
And that is only takeaway. So if this is I, this is R. Now the parallel slab, the parallel surface will make sure that this is also R. Now the same thing will not prevail in prism. The R will become R dash for the other surface because they are not parallel. So you need to apply some extra geometry or trigo relation. That's why the formula will appear differently in different topics. But if you can see the basic, you will realize that, okay, it's all same. There is no chapter. It's just a simple chapter called law of reflection and law of refraction. That's it. So now, because the eye is creating R and R of the first refraction, R of the first refraction is the eye of the second refraction.
Yes, sir.
And the next medium is similar to the first.
Yeah.
Which means whenever we have the IR pair maintained, the light ray will follow the reverse, the principle of reversibility. And you know this principle of reversibility. It will come out exactly parallel to the old one, right? This light.
Yes, sir.
So if there is no medium, the light ray would have gone this way, but because of the medium, the light ray bent here eventually, and now it will leave the medium this way. In fact, without solving, I can say this must be I. Why? The principle of reversibility. Imagine the light ray is entering from the bottom side. The symmetricity must be maintained. Yes or no?
Yes, sir.
So either you can write 2 times Snell's law and prove that this is same as I, or you just write it I. Its choice is yours. So I can write, let's say, mu medium sine I equals to mu sine R. Then I'll write it again for the next reflection. Mu sine R equals to mu medium sine I don't know. Let's say you pretend that you don't know. But from these two equations, can we write this is same as this? Yes or no?
Yes, sir. Theta is equal to 1.
So even if you pretend that you don't know, the mathematics will not spare you. It will tell you no, this is I only, which was anyway obvious because of symmetricity or the principle of reversibility. So its choice is yours. If you want to write directly, you can write directly. If you want to just exploit the law again and again and again, well, keep on doing it. Just a minute. Okay. So now this part is clear that the I must be on the other side as well. Now, because it is again I, so can we say this line is parallel to this line? So what slab has done actually? Can you guess? What slab has it done? It has shifted the light from its actual path, isn't it? Hello, hello, 1, 2, 3.
Yes, sir.
So this shift is called what? Lateral shift. So the first question that you need to solve in this chapter is, can you find the lateral shift? And the lateral shift we represent by the symbol Y. So you have simple geometry, and what is given to you, or what will be given to you, to be precise, the thickness of the slab. Now thickness will decide the shift for sure. You can see clearly, more the thickness, more the shift, isn't it?
Yes, sir.
Yes.
Anyway, your job is to use the geometry and see again, it's not physics, it's pure mathematics. If someone knows the class 9th trigo, you can work hard to get the answer. And what I'm saying is, get your answer in terms of I, R, and T, and mu. That's it. So how many refraction law we need to write to solve this question? 1 or 2?
Sir, 2.
Technically 2, but it's 1 is sufficient. Why? Because
Yeah.
it's symmetricity. So you just need to write one equation, write the Snell's law at first, and you're done. Okay. Second is, after writing the first law, Snell's law, just you think of the geometry. Okay. So use a trigo and all to get, see, you have to somehow relate Y with T in terms of I, R, and whatever you know. Can you do it?
Yes, sir.
Go ahead and tell me. So here begins the journey of geometrical optics. I will not prove any formula in this chapter. All formula you guys will prove from me. I'll give you the ideas how to do it. And then only you can enjoy the geometrical optics. Until you're not playing with geometry, there is nothing called geometrical optics. Geometrical optics is not a bunch of formulas. It's playing with the light ray, drawing the diagrams, realizing that how it will bend, how it will go, finding the nice diagram, applying the triangle property, the trigonometry, basic algebra, Pythagoras, and get your answer.
Sir, in my answer, I'm getting one part as sine of I minus R. So should I expand it or let it be like?
No, that is fine. That is fine. So keep it the way you got. So just tell me how much you got. Y equals to.
Sir, y is equal to T into sine of I minus R divided by cos R.
Very good. So that's really good. Now, when you derive the general formula or formula without any approximation, that is the first step in solving any question of optics. And once we have done this part, the next obvious step is called approximation. So in our syllabus, we have something called the near normal incidence. So JEE will always talk about the near normal incidence.
Sure, so small value of I.
Exactly. What happens if the I becomes really small, then of course the approximation will come into picture because sine, cosine, tan will follow the rule of approximation, which makes the calculation really easier. And so it is like some very predetermined intention of question setter that how to make questions or how to create formulas, which looks simple, but you need to understand that these formulas are not a generalized formula, should not be applied in any situation, only for the given situation. That's why when you derive formula in optics, you exactly know when not to apply. Okay. So for near normal incidence, I tends to 0, which means R tends to 0. There is no option, correct? And therefore the lateral shift becomes how much?
So T into I minus R by 1.
That's it, 1, correct? So now you can see that the T into I minus R is the answer. And now I can take Ti 1 minus R by I. Why I'm writing like this? We can also apply the approximation for the Snell's law. Understood? So our Snell's law was what? Mu m sin I is mu sin R, which is same as writing for, let me make it a short NNI, just in case it will save my writing effort. So we can add mu m sin, okay, mu I equals to mu R. And now you know that the R by I can be replaced in terms of refractive index, which is intensity. And therefore, the Y turns out to be Ti 1 minus mu medium by mu slab. Understood?
Yes, sir.
So this mu medium by mu slab is something which you need to know has come through the approximation derivation. It is definitely not the generalized answer. Your general answer is here. So whenever you come across a new situation, first derive the general form, and then from there you go on deriving the near normal incident relation. And you can see from this formula, which you have derived, not me, you can realize a lot of things. So let me rewrite the lateral shift y equals to ti 1 minus, you can write as mu upon mu medium. Why I'm writing this? Because this is called the relative refractive index, right?
Yes.
So we are trying to write the mu relative in the medium. So mu relative is the mu of the object which you are trying to find upon the medium in which you are trying to put. So this looks more simpler than the initial formula. And that why this is interesting that for air,
Yes,
it
sir, it becomes
automatically,
1.
yeah, the mu relative becomes the mu itself. And that is why, because before air we take mu medium as 1, the y transforms into. So again, you know when not to apply this formula. This formula is only for air, right? So always try to go in the reverse process, that a formula which you generally observe in textbook or a sheet or any coaching packages, it runs through variety of approximation and then you eventually come to those formulas. So knowing the rigorous formula is always good because you can always simplify as per the situation. Okay. So when you derive, always make sure that you derive the most general form, and from there with a series of approximation come to the formula which you like. So now the lateral shift we got, and we can clearly see it depends on three things: T, I, mu, correct? So if T will increase, Y will increase. If
Yeah.
I will increase, Y will,
Increase.
and if mu
Increase.
will increase, Y will.
Y will decrease.
If mu will increase, Y will
Increase.
increase. All will support increment, right? If mu will increase, 1 by mu will decrease, which means 1 minus something will increase, which means Y will increase. So all factor will increase, right? So after the lateral shift, which is the effect that we get due to the oblique incidence. So the normal incidence will create nothing. If I is 0, you can see there is no lateral shift. It will just go just like that. So of course, for oblique incidence, that's called the oblique when you have some value of I. For oblique incidence, the lateral shift will change. Now, what is interesting is, that if you trace back this light ray, it seems like it is coming from here, right? Actually, it is coming from here, isn't it?
Yes, sir.
So there is something called normal shift that we'll talk about. So any light ray which is coming from the nearer surface looks like to the other end coming from the different point. So this point appears to be coming or shifting here. Okay. This
Sir,
point
so
looks
it
like,
will magnify if we see from the first mirror.
no, there's no magnification, there's only shifting. There is no magnification. No, we'll come to that. So the next concept that we need to understand from the slab is called normal shift. Normal shift. How much you shift normally? Okay. So let's say again we have a similar situation. So okay, let me do the normal first. So imagine like this. Imagine the object is somewhere here. Now, if you look from exactly the other side, so a lot of light ray will come nearly. So, but all the light rays will be near normal incidence, right?
Yes, sir.
So, all the light ray is going to be the near normal object. So, what exactly happens? I have taken a generalized view. So, imagine a fish in the pond. That's better. So, this is the experimental fish. And we are trying to look at the fish from some distance here. Okay. So, we are trying to look from there. How exactly we look at the fish? Can we see the fish if the light ray will come here? Light ray cannot come here, no? Why? Because in the path of the light ray, the medium has suddenly changed, and therefore the light ray will bend, isn't it? So how the light ray must travel to reach the eye? So because the light ray will bend away from the normal. So let's say the light ray is going this way. And always remember that if I am looking at some object, the light must have traveled to me from the object. That's why I'm looking at it. So the direction of light ray we always take from object to the observer. Does it make sense, guys?
Yes, sir.
Yes.
And then what will happen? Because of the law of refraction, assuming the outer medium is rarer compared to the initial, it will bend like this. Now, what do we see? Do we see object or do we see light?
Light.
Light. I have explained this. But to form the image, we need at least two light rays. So let me draw the another light ray. Maybe I can tell this. जुगाड़ है। So see how the image and the perception comes into the mind of the observer. So the first light ray, let's say it is leaving at angle theta, and the second is making slightly more angle theta plus d theta, and these two light rays is reaching the eye. As I said, we don't see object. What we see? Only light.
Light ray.
So for me, these two are the light ray which will give the perception. So we see the light, we perceive the object. So if I extend this light ray backward, it's a very bad diagram, so I could have done a better one. So it looks like this two light ray is coming from where? This location, a location where nothing is there. So this location is called the apparent position of fish. Understood? What we call? Apparent position of fish. The position at which we apparent or it appear to be there to the observer. So we call apparent. So that is not the exact position. And in general, I mean, this diagram is not good actually. Okay, I can. What I'll do is I'll make it better. I'm not supposed to recreate the bottom. I'll give you the right picture, what exactly is happening. So generally to find the apparent position, we extend the line and we check for the line of, I mean, the point of intersection. And you can see the point of intersection is somewhere here. So our apparent position of fish is what? This is the apparent position of fish. This is the reality, the fish is here. This is the real fish. And the light from the fish after two reflection is giving you this perception. Now this is a better diagram. So you take two light ray at very small angle difference, theta and theta plus d theta. And this is the real object. But this is the object which you appear, I mean, this appear to the observer. So we call it apparent object. And the apparent object is also called the image, because image is always that is formed after the reflection has taken place, right? If you remember the definition of object and image. So light ray which is refracted or reflected whenever they meet or appear to meet, we call image position. And the incident defines the object position, isn't it?
Yes.
So for the given interface between the observer and the object, for the given interface, the light ray before is deciding the object, and the light ray afterwards, which is the refracted light, which is now reflection has taken place, will determine the image position. So because of living on a different world than the world in which the object is present, we end up feeling some shift. So there are two types of shift that we need to talk about. The object has appeared forward, or it looks like come forward. So coming forward is called lateral shift. and going upward is called the normal shift.
So like longitudinal and transverse.
Yeah, exactly. Yes. So along the normal to the boundary, if you draw normal to the boundary, this is the normal. That's why we call normal shift. Okay. So what is happening is, okay. So in general, we have to deal with two types of shift. One is called the normal shift, other is called the lateral shift. But the shift which is called the lateral shift has occurred because we are looking at it quite obliquely. You can see the fish is on the quite left side and you're trying to look from the quite right side. So more the oblique, as the oblique incidence will grow, the lateral shift will be quite a dominating feature. And that is why it is very complex to study. So mathematically, it's not easy to determine the lateral shift. In IIT-JEE 1997, they asked this question. After that, they removed the lateral shift from the syllabus itself. So the lateral shift is all about the light ray will observe quite obliquely. Now our syllabus is the normal, near normal shift, or sorry, near normal incidence. So when you try to look from this side, almost above the fish, then which shift will vanish?
Lateral.
The lateral will vanish and you are left with only normal shift. Okay. So only normal shift is required, and that you can always calculate very easily. So I'll just show you how to calculate the normal shift. Okay. So this is called the normal shift. Why? Because you can see the point which was actually here is appearing here. Because if you look from the other side, so this point, so light ray from this point is trying to reach the eye, but for the person it appears that it is coming from here. So this is the apparent position, and this is the real position, isn't it? And finding this is quite easy. How it is easy? Because finding delta n is same as finding this length,
Yes, sir.
and because we know why we can find this length, let's call it E. So what is the normal shift? Can we say the normal shift is PQ? And because why you got the answer why, can you find the PQ in the triangle which is made by the lateral shift? This
So
is
yes, sir.
normal.
I
This
and
is I minus R.
oh sorry, I minus. Okay.
So this is 90. This must be 90 minus I minus R.
Yes, sir.
So what is this angle, guys? This must be 90 minus I, no?
So y cos I
Yeah. So I
I
think
minus
you can get this angle is I
yeah.
anyway. So what is PQ? So PQ sine I is Y, or PQ sine I is Y, right?
Yes, sir.
So I'm adding deriving here only. So PQ sine I is Y. So PQ is how much? Y by sine I. Okay.
Yeah, sir.
So again, for a small angle approximation, it is Y by I actually.
Yes, sir.
So okay, I mean I will not mention here. I'll put on the next page. That's better. But this formula, if you remember this formula, that's easy. So for I will also derive the normal shift in a different way, but that is using lateral shift we can find an answer. So for normal shift, the delta n turns out to be y upon sine I using a ray diagram on previous page. So for near normal incidence, can we say something like this? For near, okay, let's write in short. So for near normal incidence, can I write delta n is simply y by I? And the y we had from one ti 1 minus 1 by mu relative upon I. Now, what is interesting that for the small angle of incidence, the normal shift will not vary on I. Normal shift is having unique value as long as I is small. So what we are getting by the way, we are getting only t minus and also we need to realize that normal shift always occurs in the sense of movement of light. So because light is trying to go up, it will go up. So this fish has shifted here, right? In the sense of movement, in the sense of light flow, right? In the sense of light direction. So the shift, normal shift always occurs in the direction of light. So for the given observer, because light is coming from top towards this observer, the normal shift will also occur in the downward direction or downward sense actually. And we have the answer. So this object will shift like this. So the shifting is very, very important. As you can see, it's a very nice formula. T into 1 minus. And this is the most useful formula that we need to know. So most of the derivation we can do using this formula. But I'll give you some easier way of doing this. Don't worry. In this chapter, if you want to learn something, just do the derivation. Okay? Nothing more, nothing less. So all right, guys, we'll continue the same thing in the next lecture. And I'll try to keep few more lectures in this week, the incoming week. So we'll try to progress this course of optics. We'll try to finish by the mid of August. So this is a big chapter. Because I'm going to cover a lot of things like optics, optical instrument, dispersion. All three things will be covered. Okay. Bye and take care.
Sir,
Sir,
So do we have to solve anything?
You can just wait for one more lecture, then you can start solving numeric.
sir,
Yeah.
so that question I sent you, question number 75.
Just let me check. Your Harshit.
Yes, sir.
Tomorrow is what? Tomorrow is Sunday. All right, guys. Okay, no, no, first I was showing your question. Harshit, no? Harshit.
Yes, sir.
Uh, the numbers. So a small block. 75. A small block of mass M and concave mirror of radius R is fitted with a stand. Okay, something like this. Anyway, stand and on a smooth horizontal table with separation D between them. That's fine. The mirror together with its stand has a mass M. So mass is equal. The block is pushed at t equals to 0 towards the mirror so that starts moving towards the mirror with a constant at a constant speed v. All right. And collides with it perfectly elastic collision is there. So in case of collision of equal mass, what happens? The velocity gets transferred, right? So
Yes.
up to d by v time. So when t is between 0 and d by v, you are approaching the mirror. Yes or no?
Yes, sir.
So at any instant of time t, you must have traveled vt. What is the distance left? D minus vt.
Yes, sir.
So what they're asking, find the velocity of the image. So your position is known to us. So what is the formula for the velocity of image? So dv by dt, if you remember the formula that we have already derived. So vi equals to, because mirror is not moving, we can write in ground from directly. Vi equals to minus v by u whole square into v object. Correct?
Yes.
And because we know the radius of curvature, we know how to write the f is also equals to f minus v. I think this is the way of writing. Correct?
Yes, sir.
So if you substitute with proper sign convention, minus r by 2 minus and the distance is a minus of d minus vt. And this is v. That's simple. So this is the velocity of the image, which is r by 2 upon minus minus plus. That's simple. So minus r by 2 then plus minus d minus v. So this is the answer for the duration before the collision has taken place. Now, once you
Yes.
collide, you collide, what will happen?
The
The
direction is changed.
no, the
So
block will be rest and the mirror will be moving with velocity v only, because it's a perfectly elastic collision of equal masses. So in the frame of mirror, the block is going left, no? Or simply say the velocity of the block is 0.
yes,
Now
sir.
this distance will be how much?
VT.
No, this will be v e minus d by v. You may ask why.
So D by V has already taken, like that
Yeah, out
interval.
of the time is measured from the beginning. So from the beginning, I have already spent d by v coming here, and then after that, whatever time is elapsed, that time it will travel x, right? So it becomes vt minus d. That's why you see the order will change here. And now you can write the formula, the same
Yeah.
formula, but you have to write I m, and velocity of image with respect to mirror means vm is minus the same. I'm writing the magnification m square. You can substitute m square, and then you can write a vo minus vm, and vm is v. The object is at rest. and then vi minus mirror velocity. Okay, this is v. So this implies the velocity of image turns out to be 1 plus m square into. So you can rewrite. Understood?
Sir, I solved it from scratch. So sir, like when I was solving, so I had a problem of writing uh, the m form, like magnification equals minus v by u. So sir, there like we have to keep, if we have unknown value, uh, and we know that it is
No, no,
going
no,
to
no, no,
lie.
no, 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 no. See, u is known to you in terms of time t, and you can find the v using the mirror formula. That's it.
Uh, yeah, sir. So sir, we have to like after that step we have to write in bracket like values of u and v, and like because it is on left side, then so we have to put minus sign. So like if we don't know value of means we have a variable, like if we have v as variable, then we don't have to write minus v and proceed, or we have to write just v.
See, v is unknown, so we don't write minus plus. We can just leave like this, and then rest we will substitute like this. You
Yes
can
sir.
see how to solve, right?
Yes sir.
Yeah, and just stick to the sign convention. You will not make any mistake. Okay. All right. So
Sir,
yeah, tell me.
sir, can you check the two answers that I have sent you?
A third one.
Mm.
Can you just say hi to me because I have lost where I is. Yeah. Okay. So which question you want clarification?
Sir, the second one. The answer is not matching.
Second one, the below one.
Oh, yes.
Okay, F2 is fine. Where is the weight part? The mg part of the cylinder. In the ABD, mg will also come.
Sir, no, I was doing buoyancy is equal to mg, right?
No, 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 don't write buoyancy. When you're writing the force as a pressure difference, pressure into area, the
Hmm.
buoyancy is not written.
Sir, no, buoyancy like F2 minus F1 is buoyancy, right?
No, that's very complex. Buoyancy, you should only write the buoyancy when you know exactly what is buoyancy. So buoyancy generally, when you write, you believe the liquid is present at the bottom layer everywhere, right? And you can clearly see here the cylinder is not like covering the water at the bottom everywhere, right? So some part is missing, isn't it?
Yes.
So if you write the buoyancy V rho G, it will be wrong answer. So there is something very, something more deeper is there. So don't use buoyancy until the object is not submerged from bottom completely.
Sir, no, I used F2 minus F1
So then you have
by
to,
like Pascal's law.
yeah, yeah. So you have to use the pressure into area. But when you're writing the pressure into area, the weight of the body should be also part of ABD. You're writing the ABD of the cylinder only, na? Cylinder.
Sir, acha, हाँ. Sir, that is not the FPD, sir. I have solved it differently below.
Yeah, but still I'm saying you try with F1, F2, and mg.
Sir, that only. But I have
And the
not drawn the
density of
mg
cylinder is,
part.
yeah. So the density of cylinder is different, no? I think it's
Rho by
given
3.
rho by 3. So if you write rho by 3 into pi r square h, the total height of the cylinder, into g, acting downward, and the topmost will be rho g h1 into pi r square something, and bottom will be rho g h1 plus h2, whatever depth is given, I don't know what is given, and then into the area in which it is touching, which is pi r2 square minus pi r1 square. You have to write a quite a lot to get the answer. Okay. Rest you can
Sir,
ask
and in
in
first one, the method is right or not? In the first question.
what is the first question? If it is free falling or it is falling with some speed less than that. A cylindrical tube with its base and
So you have to leave.
yeah, you can. So I read the question now. So they're asking beta equals what is beta? Where is beta? Oh, beta is given P1 minus P2 by root. Okay. Yeah, so if A is G by root 2, then the free surface will be parallel to the slab, the plane, right? Understood? When you move down the acceleration with a G sin theta, where theta is the angle of inclination, then the free surface of the liquid will become parallel to the inclined plane, and therefore the pressure at 1 and 2 will vanish, will be equal, because the plane, the point 1 and 2 is parallel to the given free surface, and pressure only varies as you go perpendicular to free surface. Okay. So 1 and 2 will have the same pressure, so beta will be 0. That's correct. A is correct answer.
Sir, A and C are correct.
So A is correct answer, and then C you have to find again using the basic.
Sir, no, my answer is correct. I was just asking for the method. Like my method was correct.
So why you have written P2 as rho G H2 minus rho A H2 by root 2? Next one.
Sir, because uh, if we take a elementary particle of dA and the whole liquid is accelerating downward with acceleration a by root 2, then the pressure above should be bigger than the pressure below.
Okay, that's okay. You have written okay. It's coming down. So G minus A by root 2 into H2. That's G effective, right? You could have written that.
G effective. Yeah, that.
Yeah. Okay. I thought we were writing something else. Actually, that's fine. The first part is correct. P3 will be that minus rho A. Yeah, that's also correct. If D is the horizontal length, right?
Yes, horizontal.
Yeah, along the acceleration pressure will decrease. That's correct. And P1 is like P3 plus. No, in the P1 if you're comparing the P1 with P3, only vertical height will extend. No?
In vertical height will extend, yeah, and the acceleration component is also there. So pressure
Yeah.
will
So
decrease
so
with that.
what is the vertical height? D only. It's 45 degree. And again, you are doing the same thing. Yeah, that's correct. Yes. The analysis is correct.
Okay, so
All right, guys. Now leave me for the day.